all, welcome to this lecture. Today we will derive an expression for electric field due to a dipole in case of equatorial line. In one of the lectures, the previous lecture, I derived an expression for the same electric field due to the same case, that is dipole, but on the axial line. This time it is for a case of equatorial line. I have a dipole here. One is having a charge minus q, another one is having a charge plus q. These are the two charges separated by a distance 2a. So this is the middle of the dipole. So this distance is a and this distance here, totally it is 2a. Now because of this dipole system, how much is the electric field at certain point on the equatorial line? So this is a perpendicular bisector, isn't it? So this is actually called equatorial line, perpendicular to the dipole axis. So for example, at this point, if I want to know how much is the electric field, this is actually along the equatorial line. This derivation is for that only. I'm just finding out electric field at this point because of these two charges. I mean, it is a system of two charges. We call it as a dipole. Now, let me want to find out what is the electric field at the distance r from the middle of the dipole. So this distance is r. Now, this distance obviously it is. Now you can use the Pythagoras theorem. This is 90, and even here also same. This is 90. This distance is just a square. See, this r, this is a, this is actually r square plus a square, square root. And here also r square plus a square. Now at this point P, what is electric field due to this charge? At the same point, what is electric field due to this charge? Then I may have to add them vectorically to get the net electric field. That is what I want to know. I want to know how much is the total electric field due to this dipole on the equatorial line at certain point P at a distance r. That's fine. Now let me know what is the direction of electric field due to positive charge. So you have to place a test charge here, positive test charge, and positive repulsion. So that is the direction of electric field. So this will be E plus Q. That means that is the direction of electric field due to the positive charge. At the same point, the direction of electric field due to the negative charge, you have to place a positive test charge and there is an attraction. So this way, the direction of electric field due to negative charge. This angle is theta, and as well as this is theta, same, because I am taking the bisector from the middle, so they have to be same. Now I will just resolve these two into two components. What about the net electric field here? And for obvious, the net electric field is along this direction because these are the two vectors. This is due to the positive charge, this is due to the negative charge, these are the electric field. The net electric field should be along this direction. This is actually net electric field. That is what I want to find out. This is theta, this has to be theta here, and as well as this is also theta. Now I will resolve these two E plus Q and E minus Q electric fields into two components. This E plus Q can be resolved into two components. One is the horizontal component of E plus Q, that is E plus Q cos theta. Another one is the vertical component of E plus Q, that is E plus Q sin theta. Similarly, electric field due to negative charge, that is E minus Q, can be resolved into two components. One is the horizontal component, that is E plus Q cos theta. Another one is the vertical component, this actually minus Q, right? Because I'm resolving a component for E minus Q. So that is E minus Q cos theta on the side, E minus Q sin theta. Anyway, I want to find out how much is the magnitude of electric field at this point because of this positive charge. So let me write that equation here. So magnitude of electric field at this point because of this charge at this distance, square root of r square plus a square is E plus q is equal to 1 by 4 pi epsilon naught. The charge is q, the distance square. Distance itself is square root of r square plus a square. The distance square is just r square plus a square. And similarly, the magnitude of electric field due to this charge at this point is E minus q is equal to, again, it is different. The direction is different, but the magnitude is same. So it is q by r square plus a square. So I got to know that the magnitude of electric field due to positive charge in a case of a dipole is equal to magnitude of electric field due to a negative charge. This is a trivial result I've got now. So I can tell it is just some E electric field, that is 1 by 4 pi epsilon naught q by r square plus a square. That's fine. Now I want to know how much is a total electric field. Listen to me here. E plus q and E minus q have the same magnitude. This sine theta will give you the same value. But these two vectors are in opposite direction having the same magnitude. That means there is zero magnitude, that is actually net electric field along this line is equal to 0 because these two are equal and opposite vectors. Since E plus q and E minus q are equal, this net electric field is equal to 0 along this line. So I can write, since E plus q sine theta and E minus q sine theta have equal magnitude, they have equal magnitudes, but opposite direction, they cancel. So you won't have anything along that direction. But these two are acting along the same direction, to the left. So E plus q cos theta and E minus q cos theta acting along the same direction. So these two vectors would add up to get the net electric field. So I'll write here, so net electric field, that is E vector, is equal to E plus q cos theta plus E minus q cos theta, that is definitely 2 times E cos theta, because E plus q minus q are equated as E cos theta. Now what is the direction of this electric field? So direction of electric field, net electric field, is from right to left along this direction. What is the direction of dipole moment? So dipole moment is always from negative to positive. So this is the direction of dipole moment, P cap. So it is always opposite to the electric field. So I can put it as minus P cap because the net electric field is opposite to the dipole moment. Now how much is the electric field, that is a net electric field due to dipole on the equatorial line? So I have to get E is equal to 2 into, what is E? E is here, 1 by 4 pi epsilon naught q by r square plus a square into cos theta. I don't want final expression in terms of an angle theta. I want everything in terms of the distance. So this cos theta can be written here. So I'll write here. So cos theta is equal to, so you take this theta in this triangle and you apply cos definition, cosine of that angle, that is equal to a by square root of a square plus r square. So this is cos theta. What is that? It's a by square root of r square plus a square. And the direction is obviously along P cap, but in opposite direction. Is equal to this 2qa is defined as a dipole moment. Dipole moment is equal to charge into dipole length, that is 2a. So this is 2qa or 2a into q, that is actually dipole moment, by 4 pi epsilon naught. So this is r square plus a square to the power half. This is actually power of the 1. So r square plus a square to the power 3 by 2 along with minus p cap direction. So this is an expression for electric field due to dipole along the line, along the equatorial line at certain point P at a distance r. And this means that if you take the point away from the dipole center, if you increase the distance r, definitely electric field will decrease because that is inversely proportional. Now what happens for a short dipole? What happens for a short dipole? So when can you say that a dipole is very short? When the distance from the center to the point P, that is R, is very much greater than the dipole length. If this is a case, then I can say that the dipole itself is a short. Length is very, very small compared to R, and this A can be ignored and approximated to 0. So total electric field due to a short dipole is equal to P by 4 pi epsilon naught, and this becomes 0. R to the power 2 to the power, that means R cube. So that is minus P cap. So this is an expression for electric field due to a short dipole. Again, in case of a short dipole, electric field varies inversely with the cube of the distance. So thank you for watching this.